So Ivan, can you hear me properly, for the people? Okay. Okay. So sorry for the delay. There were some technical issues. So I will straight away going to the presentation. So today, what I will be presenting is it's a recent ICLR paper, which is on like learning to segment from noisy annotation, a spatial correction approach. So this basically address one of the important issue, which is in terms of medical image and also in microscopy, so we need like experts to kind of like annotate the images, and like there are like different complex structures and everything. So it's like actually harder to annotate. And when you do that in a larger scale, like there will be like chances of getting noisy annotation. So when you do training using that kind of models, it will basically like when you train the deep neural networks, it will affect their performance. And also so mainly like why is it like very important towards medical imaging? It's that so in most of the pipelines, segmentation has been like the first step for the analysis. So if we get inaccurate segmentation of some a particular structure, so it might uh, create errors in the measurements, so which will eventually affect the downstream analysis on diagnosis and prognosis tasks. So in that case, like it is extremely important to get segmentation, but like due to the current demand, like the demand of the deep neural networks and everything, we need a larger data set with ground truth. So that kind of like some of the reasons where the annotation we get in medical image segmentation tasks have errors. So basically, like they're like the quality of the annotation kind of like depends on four factors So one would be the expertise of the person, the annotator who annotates the data set, and like most of the time it might be students who does the annotation, and like there are like chances of getting errors in that. And second one, the quality of annotation depends on the time spent to annotate the structures. So that second, and third one would be like, since like for deep neural network we need larger data sets, so there have been like large amount of annotations has been done, so which will eventually uh, create errors in the annotation. And the final one would be like it's like when it comes to biological structures, like there are like structures there, and which have like the boundaries, it's harder to like annotate, so even that might create errors in annotation. So so they have like works in this area, like to kind of like create methods to which are like robust to the segmentation label noise. So some of these methods, also they have been methods, like as we know, to handle the classification label noise. And some of the segmentation methods kind of like adapts these techniques for their task. So that's what has happened in the past work. So when it comes to classifying label noise, so for when it comes to uh, classification label noise, there are like two methods which have been explored. One is like do something like a model recalibration, and or something like a data recalibration. So in model recalibration, so what happens there is like we can develop like build some specific architectures to be robust to this kind of label noise, and also we can adjust the loss function such that it's the model is trained in a way it's robust to the noise, and also we can include something like a regularization term. So when it comes to data recalibration, like what have been done in the past work in order to achieve state-of-the-art uh, performance. So what they have done is like to do something like a data selection on on the given data set, to only select the good data set with accurate segmentation. And also like there have been methods in focusing on correcting the labels, uh, and then use those data to do the training. So that was particularly for classification label noise. So when it comes to segmentation label noise, in the past work, they have like straight away adapted the classification, the methods which are in the classification domain. So, but the key problem which have the past works haven't addressed is that the segmentation label noise, it's have different challenges compared to the classification noise. So that So this paper kind of like focus on addressing these challenges. So one would be the spatial correlation and the bias. So when you look at the images, like so the first image A, it's something like which could be like a actual true segmentation of the lungs. So what the previous works have done is something similar to B. What they have done is like they have like placed random noises, like some by like, as you know, the segmentation map would be like a binary. So they just do flipping of the pixel in random places. So which is kind of like possible like when it comes to good method when it comes to like a classification label noise. But in terms of segmentation, it doesn't actually correctly model the noise. So what the paper mainly focuses on is like they state that the segmentation label noise are kind of like spatial codices, so which means like it will be the noise will be around the boundary of the actual segment. So that's their one claim. So based on that, they build like a method to address this issue. So basically, to summarize the contribution of this paper, so the first their contribution is to present the first noise model for segmentation task. So they present the Markov model for the segmentation label noise, and the second would be like they present a method to correct that Markov label noise with the help of a smaller validation data. And the third contribution would be like they kind of like extend this algorithm so that it can iterate to handle this noise, so it can be generalized towards common label noise in the real world. So I'll be like focusing on these three contribution. So if you have any questions in between, like feel free to ask. So the first part is like I'll focus on how the authors kind of like model the segmentation label noise can as a Markov process. So just to clear, so like in this specific equation, like so specific Markov model is like a process like the next step would be only based on the current step, but not the previous step. So using that concept, like they kind of like modeled it. So the YT would like for when you take T step, sorry, T step uh, in uh, in the process. So the YT would be the segmentation we have, segmentation map we have at that time step. And using that, like, so they introduced two parameters in their method. So one would be, so one parameter is theta1 and theta2. So which is like the probabilities like they use to control whether to expand or string the boundary, and also the problem marching, which means like at what pixel points it should expand or shrink. So basically, when I expect the Z1T, it's sampled from a Bernoulli distribution. So where it kind of like states uh, like uh, whether in that particular marker, the process step, whether to expand the boundary or shrink it. So that will be given by Z1T. And the Z2T kind of like represent its Z2T, it will be like a 2D matrix. So which kind of like state in the map, like what are the areas it should string or expand. So that's kind of like given by the Z2T. And delta B, and so here they use delta B and delta F as something like they use it to define the boundaries. So delta B will be the boundary at the background. So if I will like use like give a further explanation, like showing an example. So delta B will be something like the uh, boundary at the background of the segmentation, and delta F would be like the boundary inside in the foreground of the segmentation. So in typically like the first the second part of the equation kind of like says like it's like focus on the expansion by like changing the flipping kind of like the labels in the boundary, so at specific areas. And the second part of the equation kind of like states like, so that's like z1 minus 1, which kind of like means uh the opposite of like flipping the foreground in the certain areas, so in order to enable stringing the boundary. So in order to like clearly explain, I would like to use an example. Like, so this is kind of like a 3-step Markov process. So the first one would be like the actual true marks which is there, and then so the delta F would be like the boundary in the foreground, and the delta B would be like the boundary in the background. So in the first step, like so the place when you look at B, the places which are it's expansion process. So in this case, the theta, I mean the Z1T would be 1. So only some specific and areas, only some of the areas, like some specific pixels in the boundary will be expanded. So that's kind of like indicated by the digit part. So only those pixels will be expanded in that particular time step. And also in the second step, it's also same as an expansion process. So where the ones indicated by 2, those pixels would be expanded at that point. And in the third step, like here in this case, the Z20, as I mentioned before, would be 0. So it will do the stringing process for that particular time step in a Markov process. So here, the areas which are marked by 3 are the ones which have been flipped, like which have like where the pixel, the boundary has shrinked. So this is kind of like the way they have like used modeled the label noise, which kind of like more aligned with the actual segmentation noise. So that's basically how they kind of like model the label noise one. And also in addition to this, like as I mentioned before, in similar in past work, like they have randomly flipped some of the segmentation points, I mean in the segmentation map, to introduce the noise. So in this work also, they kind of like flip some of the pixels which are like not closer to the boundary. So here for that also, they kind of like create like a noise vector, sorry, noise matrix, which is epsilon here. So they create a noise matrix to kind of like indicate in which areas, it's like a random matrix to which areas like it should flip or not. So and the sign would be like indicate like, or the, it's kind of like to give the idea, like it would be like the areas which are not closer to the boundaries, like where the expand happens. Other than these areas, like it will add the random noise into the segmentation. So by using these two, like they can like introduce the noise, and they model the segmentation label noise. So moving on to like how they propose a method to correct this label noise. So in the paper, like they kind of like more focused on the theory aspect, like how they can do this, like using a smaller validation set. So but like due to time, like I will like more focus on the method. So in the method, what they do is like first they kind of like train the deep like any model using like from using the given data set. Then they kind of like have like a small validation set, which is a clean validation set, which means like the annotations are really good there. So using that validation, they kind of like calculate a bias, which is like it's shown in this equation. So which here it's that this term would it kind of like represents the predicted mask, and this term represents the actual mask in the validation set. So and I would be, it's a cardinality of the index values in a image, and V would be the number of validation images. So using this, they kind of like calculate a bias, and then they correct the bias in the training data set. Sorry, they correct the noisy mask in the data set using this bias by deducting it from the predictions. So then using that label, they kind of like train the the model again, and they get them. So it will be like something like a iterative process there. So this is kind of like how they correct the labels by removing the bias from the noisy images. So the disadvantage, like they need something like a cleaner validation set, but also in the paper they have proved that this they can achieve good performance even with having one clean validation set. So even with one clean annotation, they can train the model well. So that's kind of like reduce the workload of the annotator. So even though there are like noisy labels, if there are like at least one image when we have the correct mask, it can be used to like correct all the noisy mask in the data set. they do use the label, label noise. They don't use the noise model, right? This one like they use a noise model like before the training to introduce to the training set. So like in their experiments, like what they do is like they use the model, they introduce the noise to the labels in the training set, and then they do the training. Here is like the labels themselves that are used to train. Yeah, we have the noise. Yeah. So they again introduce so additional noise to that training. So this one like they do that like so experiment like to say like they kind of like assume like the labels there are the good labels in order for the experiment purpose. Like in order to train a model, like they assume like the labels which are there, it's kind of like good. Like they do some techniques like to get if there are like 10 annotators have annotated one particular image, they get the intersection of all the annotation, they take it at that as the good label. So then they kind of like add this noise to that, and they see in the experiment whether their method can remove this the noise. So that's what they have focused on that. Yeah. So so that basically, so I will kind of like skip this part. So it's kind of like mostly how they model this the boundary representation as something like a sign distance function, and how they prove like they can use the validation clean validation set to kind of like remove the bias uh, from the labels. So so I'll move to the third section, like which we focus on like how can they introduce something like a spatial correction technique, like iterative correction, so which can be applied for the real world data set. So the idea brief here is like they like in the markup process, like in the noise which they have modeled, like it kind of like depends on the probabilities like around the boundary. So whether to flip, whether to string, or so it's kind of like fixed on the probability, and it's kind of like same for one instance for the time string, whether to string or another instance to expand. So, but it won't be kind of like the same when it comes to real world data. So what they argue is like they say that the real world label noise would have something like a feature dependent moving probability. So the features which we can extract for a deep neural network, it might have a dependent on that. So what they do here is like instead of applying the correction on the final output, like which means the final segmentation map, they apply it on the logits. So which is like, so when it comes to a binary, when you take a binary max, it will be like a step before getting the sigmoid. So that's how like they kind of like do some correction there in order to get the good mask. So and it has worked well. So what they do is so is the f hat x would be the logits. So before applying the sigmoid, and using that, like they kind of like change the term into adapt the bias into logits by introducing a term like lambda. So it will be like low if the bias is positive, which means like it has expanded, and it will be high if the bias is if negative. I mean negative. So which means like it has strength. So they kind of like use that term to kind of like adapt it and do a correction on the logits. So after the first iteration, they won't do any changes to the actual labels in the training dataset. They do the changes in the logits. By doing so, like they kind of like uh, do the label correction. So simply put, like their algorithm would be something like, so we have the noisy training dataset, and in addition, there's like a clean validation dataset. So first they train the noisy dataset on using so train a deep neural network on the noisy training dataset, and with using that, like they kind of like predict the labels for the images in validation, and take the uh they take the final prediction and they kind of like calculate the bias, which is like the difference between the predicted mask and the actual mask. So then using the bias, they kind of like do they kind of like do it iteratively in the loop, like where they do a correction on the logics, and then they only use the logics to do the further training. So the only the logics part, they do use it as labels in the next stage, and it will be retrained. So until it gets some acceptable performance level, they kind of like retrain the model. So by doing so, they kind of like correct the labels. So which they had advantage like over real world, like rather than just the actual how they model the data set. So moving on to research, like so they kind of like did the experiment like on like doing synthetic on the synthetic data set, which is like they use the labels which they are in the medical imaging segmentation data sets as the true labels, and they apply their noise model on that. So the first row it kind of like represent after adding the noise model. So here for this one they have used theta one, which means like they have used the expansion process only. So and the second one is the actual true marks which was in the data set. And the third one is how they corrected the mask, the final results of the algorithm. So here you can see like compared to the true mask, like it has expanded, like they have added noises around it. And when it comes to the corrected mask, like it was able to recover most, and also it was uh, remove some of the false positives which were introduced by the noise. So yeah, so similarly, like they did it for string gauge to validate, like in this step, like there were only string gauge, like it was the noise labels were string, and still it was able to correct mask up to some extent. And in terms of comparing with other methods, like so basically the first four methods are kind of like which are being used in the classification domain, which they adapted to this particular task. And the last three ones are the methods which were developed for this particular segmentation. And SC would be their method. So the metric they use to compare it is the mean of the DISCO. Uh, so their method was like they were able to like significantly outperform the previous method, and also they had advantage like with like in the noise model, with the increasing of the noise level, like their model was able to reduce correct labels better compared to the previous methods. And also when they decreased the validation size. So in this term, like there's a mismatch because the previous methods, they don't use something like a clean validation set, but like here in the validation in the iterative, they use a clean validation set. But what they do is like in terms of make it a fair comparison, you include the clean, they kind of like pre-train these methods, the past methods on the clean validation set first, and they train it on the noisy training data set. And in the training data set itself, they include the validation set there. So it has the mix of clean and noisy images or noisy labels. So in comparison that, like with even they claim like with even like one validation image, like they were able to get really good performance. So yeah, so that's basically the paper. And like so in order to summarize, like this paper kind of like propose a markup process to model the segmentation label noise, so which have not done before. And also they kind of like present like a iterative label correction approach to recover the true labels from the markup noise which they added. And also this method has a disadvantage because it kind of like requires a validation set, but they can also recover true labels even with having a single good validation image. And also it has significantly outperformed the existing method in like both synthetic and real world label noise. Yeah. So that's all. Thank you for listening. Yeah. No, so like yeah, was able to finish the paper yesterday only. Like, so I was actually thinking like whether, so in the nuclear detector we get the boundary, but like it's not. Okay, so I thought maybe there might be a problem, but like the thing is, in this case, like we might have to train another network for correction. So that's like the fallback there. But like for different tasks, we can do like for some object detection tasks in microscopy, we can use the, and if you want from there, if there's more important towards accurate segmentation, we can have a overlying additional method included in that. So that's, but I thought like whether we can recover the actual labels from that images, but like based on this method, it can't, we need something like a extra model to kind of like do the training.
I think something that's interesting is like, so we can also like inaccurate segmentation using something like threshold, like simple based algorithm, right?
Yeah.
And then if you can actually model the error that the based algorithm is making with the annotations,
Yes.
then like this becomes very powerful, like because we can just run the based algorithm on large data set.
Annotations.
Interesting.
Yeah, Tushan, like, yeah.
I think for this book, like 2 years, actually
Yeah. And also that's kind of like the hardest part when it comes to segmentation and everything. So yeah.
I'm not sure whether they can even the online technical questions from the I think you guys spoke. Any question? Yeah. Yeah. Any questions from the Zoom only audience? Yeah. If there's nothing else, I think like we can wrap up. Thanks, Jathurshan.